So Ed Merkowitz got his PhD in 2002 in atmospheric science with Fred Ressler as his PhD supervisor. He did a postdoc in astrophysics. He's an associate scientist and also director of the astronomy REU program. And he's doing some very important work on hydrogen, and it's our great pleasure to have him give us a tutorial this morning on that work. And the title of his talk is The Earth's Hydrogen Corona. Thank you, Ed.
Thanks. Okay, so can everyone hear me? So as Jeff said, I'm Ed Merkowitz from the University of Wisconsin, and I'm going to try to give you a whirlwind overview of the hydrogen corona. And there's lots of people to thank, and this list is by no means complete. But these are some people that I've been spending a lot of time lately talking about some geocoronal issues, with the notable exception of James Bishop, who passed away a few years ago. And so I'm going to use this opportunity to try to highlight a little bit of his work as well. And I'd like to thank the National Science Foundation and the CEDAR Steering Committee, Science Steering Committee, for asking me to do this tutorial. So the idea of a diffuse hydrogen corona surrounding the Earth, the Geocorona, and its possible thermal escape dates back to the 19th century. But the first real detection of this corona of hydrogen around the Earth would have to wait until the space age. So I'd say that the modern era of geocoronal research began in 1955 with the launch of a sounding rocket by a group at the Naval Research Laboratory. They detected a very strong Lyman alpha night glow in the night sky at altitudes above 75 kilometers. There was some controversy about this at first, where it was coming from. Was it terrestrial, interplanetary? But eventually, with follow-up work, it was revealed that the emission was really due to the resonant scattering of Lyman alpha off the hydrogen cloud that's surrounding the Earth. So this is not the NRL sounding rocket, but this is also another NRL experiment. Carruthers had a ultraviolet whoops, that's not the laser. Had an ultraviolet photometer that was a telescope, really, that was deployed on the moon during the Apollo 16 mission, and took images of the Earth in ultraviolet band passes, including Lyman alpha. So here we see the Earth invisible from the moon, and this is the Earth with the Lyman alpha scattering off the cloud of hydrogen. You can also see some southern polar aurora. This is the telescope itself deployed on the moon, and there's George. So this gives you kind of an idea of what the corona looks like. It's a big fuzzy cloud at the top of the atmosphere, and that's what I'm going to spend most of my time talking about. So why is this interesting? It's interesting for a number of reasons. We can learn something about the chemistry of the atmosphere by looking at hydrogen. We can learn something about escape and the evolution of the atmosphere by looking at this corona. This can tell us something about global change. And of course, the physics itself of this environment is of interest. So I'm going to spend the rest of the talk talking about this slide, which is quite complicated. And the truth is, really, I'm going to just kind of gloss over this almost completely. I put it up here just to highlight that, of course, hydrogen is part of important chemical species in the lower atmosphere, radiatively important species like water vapor and methane. And its flow through the atmosphere undergoes many reactions and changes and photodissociations. But eventually, you're left with a cloud of just atomic hydrogen at the top of the atmosphere. And so if you can say something, if you can know something about the distribution and the flow of the hydrogen at the top, of course, that's an important boundary condition for a lot of the chemistry that's happening below. Sources of methane, which is one of the important contributors of hydrogen, are farming, livestock, biomass burning. Of course, there's natural sources as well. The methane and water vapor propagate into the upper atmosphere. Most water doesn't really make it this high. It's frozen out in the cold trap of the troposphere. But water reforms again in the mesosphere with chemical reactions. And eventually, solar ultraviolet photons break this stuff up, and you're left with an increasingly dominant cloud of hydrogen at the top of the atmosphere. So evolution. Our nearest neighbors are very different than our planet. And in part, this has to do with the way the atmospheres of those planets evolved over time, the loss processes that were underway over geological timescales. And so the escape of hydrogen and the escape of components from atmospheres certainly has a lot to say about how atmospheres develop and what they look like today. You can, as I alluded to, use hydrogen to study global change, perhaps. This is a slide from Ray Robles' talk yesterday. And in the late 80s, Roble and Dickinson did a study, kind of a hypothetical scenario of halving or doubling of methane and carbon dioxide in the atmosphere, and to look at what that effect would be on the upper atmosphere. And they looked at a lot of things, including hydrogen. This is a refined version of the study that Ray showed in his talk yesterday. Here we have altitude and concentration of hydrogen from sort of an average mean state. And this scenario is if it's sort of an ice age condition, and this is the methane CO2 doubling condition. So you can see that there's a significant change in the predicted amount of hydrogen at the top of the atmosphere due to potential global change scenarios. So that's one more reason to look at hydrogen. So it's a daughter of important species, as I've mentioned. It's an important parameter in understanding the chemistry of the upper atmosphere, the mesosphere and lower thermosphere. It plays a role in planetary escape, and this is important for planetary evolution and for studying the physics of this very diffuse gas. And there's inconsistent observational evidence for hydrogen's mean state, in part because it's a difficult measurement to make from space. You need to look at Lyman alpha or beta. From the ground, there's been some problems with the Balmer alpha mission that I'll talk about later as I move forward through the talk. So let's just take a quick step back before I go any further. This is a picture that I saw on the web yesterday from Astronomy Picture of the Day, and I thought it was kind of timely given the talk I was thinking about giving. It shows the surface of the Earth, the sun's setting. You can see some distinct layers, so perhaps the troposphere, the stratosphere, and then the upper atmosphere, and then it kind of slowly falls off into space, what they're calling outer space. This outer space really is the Geocorona. The space station that the astronauts took this photograph from is sitting in the Geocorona. In fact, it's sort of at the lower end of the Geocorona. And so you can, everyone knows this, I think. You can divide the atmosphere by, in different ways by looking at gradients in temperature. So the troposphere, the stratosphere, the mesosphere, the thermosphere are basically defined by these gradients. You can define the atmosphere by different processes taking place, where meteorites are depositing sodium, et cetera, where the aurora is taking place, different layers of ionization, proton and electron densities. But you can also divide the atmosphere by densities and composition. And so these are sort of gross, large-scale regions of the atmosphere. There's the homosphere, which goes from about 0 to 100 kilometers. The heterosphere, which goes from 100 to 500 kilometers. The division between these two regions is called the turbopause. And then everything out here is the exosphere. And as I mentioned a few times already, as you get higher and higher in the atmosphere, you get more and more atomic oxygen. And I'm talking about levels of 500 kilometers or so. So this is an equation that describes the flow of species in the atmosphere. And I've divided it up into two components, really. There's this area that I've listed as important for below 100 kilometers. This part of the equation that's important for above 100 kilometers. And the main things here are these diffusion coefficients, which sort of describe how things are mixed in the atmosphere. So lower in the atmosphere, turbulent mixing, let me start again. Turbulent mixing and molecular diffusion, these are competing processes in the atmosphere. And which one of them dominates leads to changes in mixing and composition. So low in the atmosphere, eddy diffusion dominates, and we have a very turbulent, well-mixed atmosphere. I mean, we see this all the time, thunderstorms building up, things are really mixed. And this is called the homosphere because it's really well mixed. Above 100 kilometers, the molecular diffusion coefficient begins to dominate. And this tends to produce an atmosphere with species-wise density profiles. And that's why this region of the atmosphere is called the heterosphere, because things are separated basically by mass. So taking a little closer look at this equation, mg over kt you see on both sides here. This is an important parameter which is called the scale height. You can make some assumptions about this equation. You can say that, okay, let's assume there's no flow. The atmosphere is in a static state, hydrostatic equilibrium. The pressure gradient is balanced by gravitational attraction. You can assume that the atmosphere is perhaps isothermal. And so you can reduce this equation and come up with a hydrostatic assumption for the atmosphere above 100 kilometers and below 100 kilometers. So these equations in that reduced form look very similar. You can integrate and solve for the number density as a function of altitude. So I'm showing this for the lower atmosphere and this for the upper atmosphere. The subscripts here indicate that in the region above 100 kilometers, every species is governed by its own scale height. In the region below 100 kilometers, all species change their distribution with altitude with a constant scale height. So this h that I keep talking about, of the scale height, is an important parameter in any atmosphere. It's kind of an E folding distance, how fast things fall off. So basically, the smaller the scale height, the faster the decrease, as you can see by this relationship. So you can take this hydrostatic assumption, and you can make a very simple toy model of the atmosphere. You can assume that it's isothermal, gravity is constant. In the lower atmosphere, that gives you a constant scale height. You can take the US standard atmosphere values for the surface density. And then you can make an assumption in the upper atmosphere that molecular diffusion dominates, also isothermal. But the difference between these two regions is the fact that down here, or up here rather, each species has its own scale height. Down below, it's a constant scale height. And so if you plug that into the hydrostatic equilibrium equations, you can compute how things change in the atmosphere. So well mixed down here, I'm showing some minor and major constituents. There's nitrogen, oxygen, helium, and argon. In the well-mixed area, of course, everything falls off exponentially at the same rate. As you get into the heterosphere, things begin to separate by diffusive separation. And this is, again, related to the mass of the different species. So things that are heavier fall off faster. Things that are lighter fall off slower. And the net result of this is that the higher and higher you go, you're dominated by lighter and lighter stuff. And eventually, you reach a region of the atmosphere that is dominated purely by atomic hydrogen. So that's the point of the whole story up to this point, is how we get all the hydrogen at the top of the atmosphere. So the simple model didn't have any photochemistry, and it was just based on some isothermal assumptions and so on. MSIS is a model that's based on lots of observations. And so this is just a run of MSIS showing the same minor constituents that I had in my little toy model. But it also includes atomic hydrogen, nitrogen, and oxygen, which you can see are becoming freed in the photochemical region of the mesosphere. And so here we have, again, these species containing hydrogen that are broken up. At around 80 kilometers, the hydrogen density peaks in the mesosphere and then rapidly falls off as you go up. And this is sort of a constant source of hydrogen, and then hydrogen's escaping at the top. So there clearly is a flow of hydrogen for sure through the atmosphere, and my hydrostatic assumption wouldn't be a good one. Of course, the upper atmosphere is highly variable with temperature as a function of the solar cycle. And there's a temperature term in the scale height. So of course, as you go from solar min to solar max, I think I've got that backwards. As you go from solar max to solar min, you get changes in how fast things fall off in the atmosphere with altitude. So the atmosphere, in a way, sort of balloons out as solar max. So that brings us to the exosphere. The exosphere is a death metal band from Holland. But it's also the tenuous uppermost reach of the neutral Earth's atmosphere. And I suppose today I'll spend some time talking about the neutral atmosphere and not the band from Holland. So I've talked about the heterosphere and the homosphere. That can all be combined into basically the pressure sphere, the barosphere. And that's really the region of the atmosphere where atoms and molecules interact through frequent collisions. You get thermal Maxwellian kinetic distributions. Things are well mixed below 100 and diffusively separated above. But as the mean free path is inversely proportional to the number density, a level is eventually reached where the mean free path, that is the distance between collisions of atoms and molecules in the atmosphere, begins to exceed this parameter, the scale height. And when you get to that point, something interesting happens. The atmosphere can really no longer be treated as a fluid. So the exobase is defined as the level at which the mean free path is equal to the scale height. You can do some back-of-the-envelope calculations, and you really come out with a value that's fairly close to 500 kilometers. But of course, the exobase is variable, and it's really not a singly defined level, as stated here. But still, this is a pretty good approximation for dividing between the well-mixed, Maxwellian atmosphere and then the region of the exosphere where things become collisionless. So the exobase I'll sometimes refer to as RC, which is the critical level. And so that's the altitude at which you make the transition between the collision-dominated atmosphere below and the collisionless atmosphere up above. So lots of people did work on the theory of how these populations would behave in the exosphere. And Chamberlain really in 1963 took the earlier work, kind of combined it, gave a really formalized mathematical description of the exosphere and the populations that one would find in the exosphere. So he basically solved the equations for the velocity distribution that's determined by the free motion of particles in a gravitational field. And there are three main populations, depending on whether or not their kinetic energy exceeds the Earth's gravitational potential, or whether or not their trajectory intersects the exobase. And these populations of particles are ballistic, satellite, and escape. So this little cartoon just sort of highlights what these populations are. The satellite particles, well, we'll start with the ballistic particles. Ballistic particles are particles that originate from the heterosphere. They spend some time in the exosphere, but they're not traveling fast enough to escape, and eventually they make their way back down into the heterosphere. And so this ballistic population is a large component of the exosphere, and it's responsible for really redistributing the populations of hydrogen that are up in the exosphere. Occasionally, even though this is a collisionless region in the sort of classical description of the exosphere, there can be a collision. And that sometimes can put a hydrogen atom actually into a satellite orbit. So the hydrogen atom is no longer returning to the heterosphere. It's actually rotating around the Earth like a satellite. And then, of course, there's also an escape component, which maybe is not on here. And the escape components, of course, are those particles that are leaving the atmosphere altogether. So neglecting collisions, a particle moving vertically upward will escape the Earth's gravitational field if its kinetic energy exceeds the potential energy. So you can solve this, and you can find that the escape velocity at 500 kilometers, the nominal exobase, is about 10.7 kilometers a second. For a gas in thermal equilibrium, you can compute the most probable molecular velocity. And if this velocity is much greater than the escape velocity, then the atmosphere is going to flow off like a fluid, which is indicative of the solar wind. But for the present-day exosphere, this is not the case. So our atmosphere is not flowing out like a fluid. But if you look at the population, the thermal population of atoms, there are some fraction that have velocities that are larger than the escape velocity. And so it is possible for hydrogen to escape. So the maximum thermal population of escaping atoms occurs near the exobase. This is because you need a density that's high enough to maintain a significant collision rate so that you can get some particles with a high velocity. But the density also has to be small enough in the vertical to permit these particles to actually escape. So once they get the high velocity, you don't want them to hit something else if they're going to get out. And you can calculate the thermal escape flux dating back to Jeans and others, which gives you a value of about 7 times 10 to the 7th atoms per centimeter squared per second as the escape flux. But in order to escape, hydrogen must first actually get to the exosphere or the exobase. And that's dominated by its flow through the lower atmosphere. And this actually sets up a limit and might actually be the actual driver behind what the escape flux is. And this work goes back to Hunton in the 70s, who came up with this idea of, Hunton and Donahue and others, who came up with the idea of the limiting flux concept. They made estimates based on chemical models mainly of what the flow of hydrogen would be from the mesosphere photochemical peak region. And they found that it implied an escape flux of about 3 times 10 to the 8. So it turns out that this thermal Jeans escape flux is low by a factor of 2 to 3 or so. The other interesting thing that these studies revealed is that this value, this 3 times 10 to the 8, seems to be constant over a solar cycle. So thermal Jeans escape is a little bit too low, and these limiting flow concepts seem to indicate that there is a constant flux of hydrogen from below and constant over a solar cycle. But of course, the temperature of the upper atmosphere really changes with solar activity, and the Jeans flux is called a thermal Jeans flux because it really depends on temperature. As the temperature goes up, the Jeans flux increases. And so constant escape flux is a bit of a mystery in terms of just purely the thermal Jeans escape flux. So that led to the work by Tinsley and others. Tinsley, using the charge exchange reactions of coal, came up with the idea that perhaps charge exchange and later the polar wind would be responsible for making up this deficit in the escape flux that we see from just Jeans escape. And so what happens is you have a hydrogen atom, and it interacts with a really fast-moving proton. The electron goes to the fast-moving proton, which then becomes a really fast-moving neutral. And if it's going in the right direction, it escapes the atmosphere. This reaction can go both ways, but it's probably favored in this direction. The other reaction that can also go both ways is between a proton and oxygen, changing an electron. And in this direction, which is probably dominated in the polar regions where there's lots of O+, a hydrogen atom becomes ionized, and then it's free to escape the atmosphere on open magnetic field lines. So these two processes, combined with Jeans escape, look like they could give you an escape flux that's constant over a solar cycle. Here we have Jeans, which is increasing with exobase temperature. Charge exchange actually goes in the opposite direction with temperature because you need a little bit higher densities. And so if you look at the total, it's sort of flat. This figure that I'm showing here comes from Helen He's thesis with Bob Kerr from the 90s. OK, so back to this NRL rocket flight that I started with. This is the paper that showed the data from the rocket flight. And here we see contour maps showing the Lyman alpha intensity that was seen by the NRL group. And there's a minimum here, which turns out to be, no one can probably read this, but it's in the anti-solar direction. And so it looks like the distribution, the intensity distribution on the sky from this rocket seen at night was peaked as you get closer to the sun and less intense as you move in the anti-solar direction. So I'm just going to take a moment here to talk about some different methods that people have used to study hydrogen. This is a little bit of an aside. Hydrogen has been studied in the upper atmosphere by mass spectrometers on various AE satellites. H derived from in situ mass spectrometer measurements of H+, O+, and O, and assuming charge exchange at equilibrium, which is, I guess, maybe valid below 400 kilometers or so, are the basis of hydrogen in the MSIS model. Lyman alpha and Lyman beta have been used from satellite observations to also study the hydrogen geocorona. And what you can learn from looking at Lyman alpha and beta really depends on the satellite itself, its orbit. If it's hanging around mostly near the exobase, you're in a cloud of scattered emission. And so you really can only say things about the critical density at the exobase, NC, or the temperature near the exobase. If the orbit is elongated and spends time near the exobase and out, you can actually look at the profile, the density profile of hydrogen. And this was done by Anderson using some AE satellite data from the 70s. And Bush and Chakrabarty and Bishop also looked at this data set. And this data set maybe is considered the gold standard for the hydrogen density profile derived from satellites. You can also look at this emission from the ground, and I'll get to that in a second. People have also studied the hydrogen geocorona using absorption cells, and I'm not going to say much about that. I guess I should also say at this point that the hydrogen distribution that I'm talking about is really in the thermosphere and the exosphere. Of course, this all begins in the mesosphere and the chemistry below, but I'm not going to talk about mesospheric measurements really at all. So I'm just going to focus on the observations from the thermosphere and exosphere. Oh, I should point out that this work seemed to indicate that there was a diurnal variation in the exobase density, with a maximum occurring in the morning and a minimum late into the night and a maximum near the morning. And the Lyman alpha observations that determine this value are consistent with some of the mass spectrometer values that also measured a diurnal variation in the hydrogen near the exobase. So this is just an EMSIS run, just a generic kind of run showing the exobase number density as a function of local time. And this is indicating what I just said was noted from observations, that there's this density maximum and then a minimum down here. This is also just a generic EMSIS run giving some indication of what the temperature variation might be like at the exobase. This is actually in terms of kilometers a second. I'll tell you more about that later, but you can also think of this as an actual temperature, maybe 800 Kelvin or something like that, as a function of local time. So there's a minimum in temperature, which seems to correspond with the maximum in density. So the exosphere cools, maybe the density piles up, but also the escape flux changes a little bit because the genes escape in particular is dependent on the temperature, and so maybe there's less escape also in the night. So I've mentioned the Navy's, the NRL's sounding rocket that looked at Lyman alpha. About the same time that Lyman alpha was detected by the NRL rocket flight, observers on the ground also detected Balmer alpha in the night sky, really within the same year. Balmer alpha night glow is the result of Lyman beta scattering off the hydrogen in the Geocorona, and it leads to something called Balmer alpha fluorescence about 12% of the time. So just to remind everybody, the Lyman series is when you go from the ground state of hydrogen up to n equals 2, that's Lyman alpha, n equals 3, Lyman beta, and so on. The Balmer series is from the 3 to 2 transition, the Balmer alpha series that is, and Balmer beta, which I'll also talk about later, is from the 4 to 2. Balmer alpha is excited by Lyman beta, so Lyman beta from the sun hits the hydrogen in the Geocorona, excites it, and then Balmer alpha is emitted 12% of the time. The rest of the time, it just drops back down, and you get Lyman beta emission. So this is an example of some of the very early ground-based work. It's not the first observation, but it is the first observation that was done with a Fabre Perez. And I think that's important because Fabre Perez really changed the way we could look at the hydrogen Geocorona from the ground. And I'll say something about that in a minute. They were able to get useful Balmer alpha signals from the night sky in integration times of an hour or less. This was a significant improvement from some of the earlier work. They see that the distribution actually is markedly asymmetric, with the morning densities higher, or the morning intensities rather, higher than the evening. And so what you see plotted here is the intensity of the emission that was measured, the Balmer alpha emission, as a function of anti-solar direction. And so it's plotted in the reverse, but let's just assume that the sun's setting, the intensity seems to go down to a minimum, and then it comes back up, although this is morning and this is evening. This was done by Sheglov in Moscow. So the Fabre Perez, why did I highlight the paper that used the Fabre Perez? It has everything to do with a concept called throughput. Fabre Perez can let in lots more light than a slit spectrograph. A grating, for instance, the spectral resolution that you get with the grating is proportional to the slit width. And so if you want to get to higher resolutions, you have to make the slit narrower. Of course, you narrow the slit, you're letting less light into your instrument, and so that's a competing factor. You have to integrate longer to make up for that. A Fabre Perez, though, you can actually, because of the way light is dispersed, you can really open this thing up and let in lots of light. And for a diffuse source like the Geocorona, something that fills your field of view, this is really important. It means that you can really open up the system. I mean, if you're looking at a star or something, you could make arguments that, you know, which system will be better. But for a diffuse source, Fabre Perez, they win all the time. And so the use of the Fabre Perez by Sheglov and then almost everybody else after that really allowed a lot of things to be learned from the ground about the Geocorona. So back to this plot, I mentioned that there was a minimum in the anti-solar direction, and then it came back up. It's a solar excited line, this Balmer alpha emission. And so if we look at the sun illuminating the Earth, on the night side of the Earth, if you're on the terminator, the sun's maybe just below the horizon. you're getting very bright emission because lots of the atmosphere is illuminated. As you go deep into the night, you get less and less emission because higher and higher regions of the atmosphere are illuminated, and there's less and less stuff to make the Balmer alpha emission. And so to first order, the base of this column emission, this shadow altitude, can be used to study the altitude structure of the Geocorona. So I'm jumping ahead a little bit in terms of ground-based observations, and this is some work that was done at Wisconsin by Ron Reynolds and Fred Ressler and Frank Scherb. They were actually, after studying the hydrogen emission from our galaxy, which at the time people thought was confined to very small regions, but there was some evidence that it might be really widespread in the galaxy. And so they used a Fabre Perez to make high-resolution measurements of the night sky. And this is two plots here showing the same portion of the sky but taken some time apart. Here you see sort of one bump in January, the same region of the sky, the same coordinates. You get a distinct splitting. And this peak is markedly narrower than this. It turns out that this is galactic hydrogen emission. This is hydrogen emission from the Geocorona. And they're separated by the fact that the Earth is moving around the sun. That introduces a Doppler shift between the rest frame, which is basically the hydrogen in our atmosphere, and the galactic emission. And so this slide also reminds me that I'll almost exclusively be using a velocity scale instead of a wavelength scale in more traditional units like angstroms, in part because it's really useful for exploring these spectral shifts. But you can easily convert back and forth through this Doppler relationship. So Reynolds' work led to an all-sky map of hydrogen in the northern hemisphere. And the southern hemisphere is actually being filled in now. And so you can see that there's galactic hydrogen everywhere. And so this is a complicating factor for looking at hydrogen from the ground. You have to really be careful where you're looking and when you're looking. As you move towards, this is in galactic coordinates, okay? So this is the plane of our galaxy. There's lots and lots of hydrogen in the plane, and these are the poles of the galaxy. So this is kind of what you'd refer to as, I guess, the Milky Way if you go out on a clear night. Up at the poles, of course, there's less hydrogen, but almost everywhere you look, you can still see signal. So kind of a weird stretch, but you can see that there's some emission up here. And not only is there emission everywhere, there's multiple components to this emission. Our galaxy is rotating. If you look towards the galactic center, you see a component near zero, which is kind of the local interstellar gas. But you also see a Doppler shifted component from the next spiral arm over. And if you look toward the outer part of the galaxy, you see multiple components as well, also Doppler shifted. So you have to be careful about where you're looking, and you also have to be careful about what side the Doppler shift might be on and what the component structure of the galaxy is if you're really going to do a good job interpreting Balmer alpha observations. So back to line profiles in general. The area under a line, so this is think of this as intensity and wavelength. You have a spectrograph, you get a line profile. The area under this line is proportional to the intensity in some way. You can look at the line width. It turns out that the line width is related to temperature. That EMSIS plot I showed was a temperature in units of kilometers a second, and that was obtained through this relationship. For hydrogen, this all reduces to 7 times 10 to the minus 7th times whatever the rest wavelength is, and you can compute temperature from line width. This is, of course, making the assumption that things are in thermal equilibrium, that your population is a Maxwellian population. You can also look at the line center and look for Doppler shifts in the line center as well. So that takes us to the 80s for some other work that was done with the Fabre Perez. Merriweather built on some observations that were done by Atria, I think first in Michigan, then later at Arecibo. They had a Fabre Perez that was working at fairly high resolving power, high enough resolving power to actually resolve this line width. So some of the earlier, all the earlier observations were just intensity. They had no line width information. But starting with Atria and then later with Merriweather, you could look at the line width itself. So now for the first time, you could actually use the Geocorona Balmer alpha emission to look at temperature variations. And that's what's plotted here. Here we have temperature in units of Kelvin and local time, time, going from evening to local midnight and then into morning. And you can see that there's a marked narrowing of this profile with time. So at the midnight scans, the line width was the narrowest. And if you remember me talking about shadow altitude, this is the highest shadow altitude. So there seems to be a narrowing of the profile with shadow altitude, the highest regions of the atmosphere being illuminated. This is jumping a little ahead to some theoretical work done by James Bishop and Chamberlain. They looked at synthetic profiles and tried to understand what a ground-based observer might see in terms of exospheric particle populations. These, I don't want to spend too much time on this, but we're sort of stepping out in distance from the Earth. So think of this as very high shadow altitudes, and this is very low shadow altitudes. And so there's a prediction here of a narrowing of the profile as you become dominated with a satellite population of atoms, for instance. But there are other reasons why the profile could be narrower, and it really requires some detailed radiative transport analysis to understand those details. Keeping with James' work, James, for his PhD with Joe Chamberlain, refined the analytical model that Chamberlain developed in 1963. So he took this idea of the ballistic and satellite and escape particles and added what effects the ionosphere and interactions with the plasmasphere would have on the satellite populations. And so he accounted for radiation pressure and the loss of satellite population and the production of the satellite population. And there's a very nice series of papers numbered 1, 2, and the previous one I showed is 3, talking about really the state of the exosphere and the state of the art of the physics at the time. So that takes us to some work that's taking place now. These are some instruments that I'm associated with. This is the Wisconsin H-alpha mapper that looked at that galactic hydrogen that I was showing you, but we also use it for terrestrial emission. We recently moved it to Chile. I'm kind of excited about that because there's lots of aeronomy going on in the Andes these days, and so it's kind of fun to have an instrument nearby now. And this is our observatory at Pine Bluff, which is near Madison. Very quickly, both of these instruments are also Fabre Perez. They're dual etalon Fabre Perez, which is very useful for extending the free spectral range. It turns out that a Fabre Perez has a periodic interference function, and if you really want to look at lines, it's nice to have a cleaner free spectral range, and this helps, and it suppresses some of the background. We use a CCD imager and this ring summing technique that was developed by Coakley, and it's really led to tremendous improvements from ground-based observations of geocoronal hydrogen. I won't say too much here other than WHAM works at a slightly lower resolving power than Pine Bluff. So this instrument can look at the line profile, it can measure temperatures. This instrument really can only look at intensities, but it's extremely sensitive. So what do we see these days when we look with the Fabre Perez? This is an example of some of our data. Here we have this parameter shadow altitude that I introduced and intensity. This is the evening and the morning. If you overplot these two, you see a distinctive split, and so we're actually seeing a difference in the observed intensities, which is clearly related to the underlying hydrogen population with intensities higher in the morning, just as the mass spectrometers and the Lyman alpha work from space indicate. With the Pine Bluff instrument, we, as I mentioned, can look at line profiles as well. So this is Doppler width, which you can think of as temperature. And this is shadow altitude going out to 20,000 kilometers and then coming back up into the morning. So this is a couple years of data near stellar maximum that are just overplotted with a very simple linear fit because it looked pretty linear to me. And there's about a 500K decrease from about 850K near the exobase, 500 kilometers, down to about 350K out at 20,000 kilometers. So, something that I've been spending some time on lately is taking all this Doppler line profile data and taking a careful look at what the line widths are saying in the exobase region. So I'm making a cut here at around 1,300 kilometers. So it's above the exobase, but it's an area of the atmosphere that, if there's any area of the exosphere that's going to be dominated by ballistic populations, it's going to be these lower regions. And so if you collect all the data in the lower regions near the exobase and look at how that changes over months and months of data, 2 years of data actually, and create an average of what the temperature is telling you in these exobase regions and plot that data, you get this. So here now I have temperature in real temperature units, not kilometers a second. Here I have day number from 0 to 365. So there's 2 years of data here plotted, and this is just the temperature that's derived from the Exobase observations of the Balmer Alpha line width. The open points were collected in 2000, which was really pretty close to solar maximum. The filled-in points were collected in 2001, also still pretty close to solar maximum. And they're overplotted. So this structure that you see here, this kind of double bump, is 2 years of data observed from Pine Bluff. Overplotted is an EMSIS run of how the exobase temperature would change at a fixed time over 365 days for an F10.7 value of 70. The F10.7 value of 150 is a little closer to the exobase conditions at solar maximum. And so you can see right away that the line width that I'm observing is cooler than the temperature predicted by EMSIS. But sort of qualitatively anyway, the shape looks pretty similar. So we're definitely seeing this sort of double peaked structure in the temperature variation. And so this needs to be explored further. I probably didn't mention this, but the ground-based observation of Balmer Alpha is a column emission. So although I'm trying to dominate my signal by the emissions from near the exobase, I am seeing the entire column. There's also multiple scattering of this emission into the Earth's shadow, which could be illuminating cooler regions of the thermosphere. And so these things need to really be addressed by looking at our radiative transport model to make a conclusion about what the neutral temperature is from this data. But I'm really encouraged by the trends that I'm seeing. And the fact that these data points right here and here and here are a year apart really gives me some confidence in this data. So I mentioned that you need a radiative transport model. Luckily, we have one. James Bishop developed a computer code called LYAORT, which is based on some radiative transport code developed by Anderson and Horde. It's basically in a logarithm that will predict observed intensities, radiation distributions, and scattering. And then you can calculate what the observed line of sight intensity should be using this model. It uses the complete frequency redistribution approximation for those of you who do that kind of thing. It's a spherically symmetric model, but it's non-isothermal, so it takes into account the fact that there's temperature changes. James used this model and some data that was collected in Hawaii by John Harlander in the 80s, and he applied the RT modeling doing this non-isothermal Lyman beta radiative transport and updated line center estimates. The sun is exciting this, so you need to know what the sun's doing. And some corrected thermospheric atomic hydrogen density profiles. And he got an excellent fit to this data set that was consistent with satellite observations. So some people in the audience might be familiar with something called the factor of 2 problem. There was this discrepancy between ground-based data sets and satellite observations. This work by James really seems to show that that's no longer an issue. The updated transport codes, what we know about the sun now, and corrected hydrogen distributions put the factor of 2 problem to rest. You can get agreement between ground-based and satellite-based sets of data, which will be important for something that I will try to get to. So this code developed by Bishop in the 90s, LYAORT, as I mentioned, is a spherically symmetric non-isothermal RT code. It generates global source functions and apparent column emission rates. You can feed this code any model you want, but it has the possibility of giving it a parameterized hydrogen distribution, and this will be important for something I'm going to talk about next. So you can define an exobase density, a mesospheric peak density. You can define the flux from the mesosphere to the exobase. You have to propagate this flow of hydrogen through some kind of background atmosphere, and so that's done using EMSIS. And then the hydrogen itself is extended way out into the exosphere using the updated analytic model of Bishop, which was based on the earlier work of Chamberlain. So the parameterization that James came up with for the hydrogen profile is not really shown here. This is an EMSIS profile, but the parameters are. So this is number density, and this is altitude. Here we have the peak of hydrogen in the mesosphere, and then it flows off out to the exosphere. Phi is the flux that's coupling these 2 points, and then the exospheric distribution is up here. So if you take some data from WHAM and you take James' model and you do some runs, you can see that you can get some really interesting agreement. So what I'm showing here is some WHAM Balmer alpha data that was collected when WHAM was at peak. This axis down here is shadow altitude going from 0 kilometers out to 6,000 kilometers. And this scales intensity in Rayleighs. I'm zooming in on a set of points here. You can see that there's some diamonds and some X's, and that there's a slight mismatch between the two. That's actually observed changes in intensity due to viewing geometry. So these are really small effects, millirayleigh in some cases. So the sensitivity of WHAM allows you to really probe the intensity distribution as a function of viewing geometry. And what's maybe more remarkable is James' model can actually predict that. So here we have observations that show this little discontinuity due to changes in viewing geometry. Here we have a model run that shows the same sort of discontinuity. And so there's really becoming a handle here to take these observations and to take these models and retrieve a hydrogen density. That's the goal. There's 2 runs with the model done here. One that was a fit to the data, kind of a chi by eye sort of fit, just messing with the parameters to get a good match, not a unique solution, to be sure. But the underlying distribution is just a straight EMSIS run. So if you took the hydrogen as it is in EMSIS, computed intensities with Bishop's code, compared them to the observations, they don't agree. And I'll say more about that. I guess I'll say more about that now. This is some work that Susan's doing, where she's just taking hydrogen distributions in the EMSIS model and the TGCM model and computing intensities using Bishop's code and then ratioing them to WHAM data for the same look directions. And so you can see perfect agreement, of course, would be 1. There's one case, actually, that seems to show fairly good agreement. But the other cases of the models show distributions that are inconsistent with the intensity observed from the ground. This is really no surprise, okay? I mean, the EMSIS model has data that's probably fairly good to around 400 kilometers, maybe, from in situ mass spectrometers. But then diffusive equilibrium is assumed above that. Not very much work has been done to try to really put the physics in the model to get the hydrogen distribution in the upper atmosphere right. I mean, a lot of the photochemistry below is probably in good shape, but how that stuff propagates up needs some work. Something else you can do with long-term data sets is look for variations in the emission, and this is a continuation of some of Susan's work at Wisconsin, where she's looked at the emission intensity as a function of year. So here we have intensity, here we have year, and you can see that there's a peak in the intensity and then a dip, which corresponds to solar cycle, this being solar max. So our goal is to take this code of Bishop's and our observations and this parameterization that he came up with and do a forward model approach to try to actually retrieve useful geophysical parameters. So we no longer are interested in just how the emission intensity is varying. We really want to try to get out the density at the exobase, the density in the mesosphere, the peak region, and the flux between these regions. James and I did a trial run of this. We set up a very coarse grid where we varied these parameters, the hydrogen parameters in the mesosphere, the exobase, and so on. We used some different solar geophysical conditions, and we ran lots and lots of cases, 60 or 70,000 cases, and then matched them to our data to look for good fits. But not only the ground-based data, it turns out we had some satellite data of Lyman beta as well, and so we fit both of these emissions at the same time and looked for a self-consistent fit between the Lyman beta rather, and the Balmer alpha data. So line of sight intensities were generated for each of these pointings, and we did this comparison trying to match the shape of the curve in both of the observations. And so these are the retrieved distributions that we got. As I said, our parameter space was very coarse. We weren't trying to get a unique solution. We were trying to demonstrate if this kind of forward model approach would even get us anywhere. And we were sort of satisfied with the results. We definitely got a range of solutions, and they're sort of quantized because of the way our grid spacing was set up. But in all cases, in the lower atmosphere, they're very different than EMSIS. And I think this is in part due to flow of the atmosphere, the hydrogen from the mesosphere up. So where we're headed with this is we're going to use some WAM data and Pine Bluff data and look at two different emissions, Balmer alpha and Balmer beta, which have different scattering properties. They see different layers of the atmosphere, so they see different density distributions. If we can model both of these emissions at the same time, I think we have a good hook to retrieve a hydrogen density. So this is some data that was taken in 1973 by Reynolds. I showed that paper earlier. This was sort of state of the art at the time. This is into solar depression angle, sort of, but you can think of this as time of night, really, so midnight over here, evening, morning. Balmer alpha and Balmer beta. There's a few points, lots of scatter. It took lots of time to make these observations, hours or more. This is WAM data. Each of these exposures were taken in 30 seconds. This is also time, so here's local midnight, Balmer alpha and Balmer beta. The differences you see in the groups of points are due to different look directions, so viewing geometry effects becoming apparent in the intensity. And so we can model these things and use the scattering properties of the different emissions to try to retrieve the hydrogen distribution. So there's other groups doing great work with hydrogen. There is some photometers and Fabre Perez, and Fabre Perez that's recently been refurbished at Arecibo. And they also have a long-term data set, which I'm not going to have time to go into too much detail. Arecibo, of course, is by a radar, and so you can do some interesting things, especially if you can get the hydrogen distribution. This is an example from Lara Waltrip, where she used Arecibo data and some retrieved hydrogen data from He to try to get the oxygen population using charge exchange equilibrium. The data from He probably wasn't good enough. I mean, that was because it was a photomultiplier and things have come a long way. And so I think that this kind of study can be done in the future. Not only do we have these ground-based data sets, GUVI, until recently anyway, was doing limb scans, and so there's GUVI data as well. So it's a really exciting time to look at the Geocorona because we can look at it from multiple wavelengths. We can combine these wavelengths with forward modeling approaches, and we can then use that information to retrieve the hydrogen density. And there's also modeling work that's being led by James Crowley to update the hydrogen flow in these models. And so I think the data combined with the modeling work that's done can really bring this hydrogen problem to closure. So I think I'm really close to out of time, so I can stop there, yeah. So thanks.